Okay, good morning, students. Am I audible to all? Please put it in chat box or otherwise someone unmute yourself and tell me. Okay, yes. PPTs are visible? PPTs are visible? Yes. Okay, thank you. Very less students are joined today. Okay, now in second unit, last topic is remaining. That is in IEEE standard, second type, that is a double precision format. So in previous lecture, we have seen the single precision format. Now in this lecture, we are going to see the double precision format. In the double precision format, there are 64 bits are there. That 64 bits start from the bit 0 to the bit 63. Total 64 bits are there. Out of that, 52 bit is used for the mantissa. So 52 bits, that means start from the 0 to the 51, total 52 bits are there, which is used for the representation of the mantissa. Now, next block is for the 11 bit of exponent, which will be start from the bit number 52 to 62. That is total 11 bit, which is used for the representation of exponent. Now, next one is 1 bit sign bit. S indicate the 62 to 63. That is a 1 bit used for the sign bit representation. Now, in this sign bit representation, there are two types of sign bit which is used for the representation of the particular data. If this sign bit for the given number is positive, then the sign bit value should be set as a 0, and whenever the sign bit is having negative number for the given decimal number negative, then this sign bit will be set as a 1. That's it. That is a to identify whether that given bit is sign bit or not, or that is a, you can say that the given number is positive or negative. To represent that thing, it is used. Now we will go for the directly method for the double precision. Already we have seen that the single precision in the 23 bit is used for the representation of mantissa, 8 bit is used for the exponent, and 1 bit is used for the sign bit. Now same thing is we have to go for the double precision. Now in a double precision, we are having the 52 bits of the mantissa, 11 bits of exponent, and 1 bit is used for the sign bit representation. Now we want to solve the problem of double precision. In that, this PPT indicate the number of steps which is we want to follow for the solving the double precision format. In that, first step is that first is convert a given decimal number into the binary. In that number may be a consist of floating point number. In that case, integer separately and floating point number or fraction part separately. We have to convert that given decimal number into the binary number representation. That is the first step. Then after performing that steps, we have to find out the answer given decimal number in the binary. Second step we have to go. In that we have to go for the doing the decimal point either left side or right side, and it should be have a 1 point something value like that we want from the, if you move for the left side, that is a positive, and if you move for that decimal point right side, that is a indicate the negative of the exponent value. It will be give you exponent value mantissa and sign bit nothing but the whatever number is given at the beginning of that particular number. We want to find out the double precision whether it is a positive or negative. It will be indicated with the help of that. Now third one is, if the given number is positive, then we are saying that it is a sign bit, we need to set value 0, otherwise sign bit value that particular number is negative, sign bit value we need to set as a 0. Then we have to go for the fourth step, that is a biased double precision format. In that formula is that E dash is equal to E plus 1023. This formula we have to apply, but in single precision, if you are having the all steps are same, only difference is that in that E dash is equal to E plus 127. Access code of 127 is taken. But here in double precision, for the exponent value, we are taking the access code of 1023's access code of exponent is will be taken. That's why this equation is coming for the double precision. After finding the value of E dash, which is in decimal, again we need to convert into the binary. That we have to done in we have to do in fifth step. Now in sixth step, we need to put the all these value in the form of the double precision. That is a single bit is used for the S, then 11 bit is used for the exponent, and the 52 bits are used for the mantissa. Like this data we have to represent, that will be the final answer of the double precision. Now moving to the actual problem statement. Here problem is given that to represent the following number in a double precision format. Number is given in a decimal 100.125, which is given in a decimal. So according to double precision formula steps, convert the given decimal number into the binary separately and fraction parts. So out of these 100.125, out of this 100 is integer parts. So whenever we are converting any decimal integer number into the binary, we need to perform the divide by 2 operation like this. 2 divided by 100 and keeping the track of the remainder here in the last column. So we have performed this 2 divided by 100. So 2 5s are 10 and 0 as it is. Remainder is 0. Again 2 2s are 4. Then 1 is remaining. 1 0 it becomes. So 2 5s are 10. Remainder is again 0. Again 2 divided by 2. We can get 1 and 2 2s are 4 and 1 is remainder which is kept here. Again 2 divided by 12, we can get this, remainder is 0. 2 divided by 3, 2 divided by 6, we can get the answer and remainder is 0. Again 2 divided by 3 is 1, means 2 ones are 1 and remainder is 1. And we are keeping the, according to this arrow positions, all bits we are keeping. So we can get for the 100 binary representation is 1 1 0 0 1 0 0. Now for the fraction part, 0.125 multiplied by 2. So we have to perform the multiplication. We can get the answer 0.250. Again 0.25 multiplied by 2. We can get the answer or 500 or 500 multiplied by 2 is again 100. We are getting 1.00 answer we are getting. Now in a fraction part, whatever integer value is coming here in a after multiplication, that is here 0.5, 0 we are going to take, 0.500, 0 we are taking here, and 1.001 is taking. That will be a 1.125's binary representation is 001 that we are getting. So for this given number, we are getting the binary value, that is a 1 1 1 1 0 0 1 0 0, and after that for fraction we are getting 0 0 1. So 0 0 1, that will be answer for the 100.125 decimal number presentation. Now we move to the second step, that is a normalize the binary number and find out the value of sine, exponent and mantissa. So what do you mean by the normalization? We have written the these decimal numbers binary representation, which is we are done in a first step. Now we are moving decimal point from this location to the after 1. So how many digits we are moving to the left? 1 2 3 4 5 6. So 1.100010001 multiplied by 2 raised to 6. So this will be a normalizations which is we had done here. After representation of the normalization, we need to find out the values of sine, exponent and mantissa. Here sine value, here sine value, how we are going to find out whether given number is positive or negative. Here given number is positive, so sine value I am going to set which is a 1 bit. So it should be set as a 0. Exponent value we are getting 2 raised to 6. This will be a exponent, which is I have written here exponent value E is equal to 6, and M indicate the mantissa. Mantissa is nothing but the after fraction value, whatever data is there, that will be a mantissa. Here in this case 1 0 0 1 0 0 0 0 1. This will be a value for here. I think I missed 1 0. And then 1 is should be there. Then that will be a mantissa we need to represent. After performing this, we go for the next step, that is a bias double precision format. Bias double precision format For that, formula is that E dash is equal to E plus 1023. What is this 103? That is a access code of 103. Access code of 1023. That is a access code of exponent, which is represented in a formula itself. So we need to find out the access code of that particular number. That means we are adding that value into the access code. For example, n value is there. What is E is having? That we need to add in this 1023. That will be give you access code of 1223. So here E value is 6, which is mentioned here, and we need to find out 6 access code of 1023. So I'm adding 6 plus 1023, which will give me access code of 6 in terms of the access code of 1023 of 6 is I'm getting 1029, which is also result in a decimal. Now fifth step is that again I need to convert E dash into the binary number representation. So when this total number is totally integer, so what I need to do for the given decimal number, I need to perform divide by 2 operations and keeping the track of the bits in this position from the downside. It is a 1 is there, then 5 times 0 1 0 1. Then after that this steps is completed, then we move to the 6 number steps. In that we need to put the values of S, that is a sign bit, E means exponent, and M means the mantissa in a double precision format. Now S is having value 0, which is of 1 bit. Exponent is 11 bit. So exponent value we are getting here the 1 1 6 times 0 1 0 1. That value I have written here, exponent value, and mantissa value we need to take from the step 2 after the fraction part 1 0 0 1 triple 0 1, and total here mantissa is 52 bits, but in our answer we are getting only 8 bit mantissa. Remaining bits 52 minus 8, total we can get the 46 bits are remaining. For that bit, number of bits 46 bits, we need to put 0, either 0 or you can put the dot dash dash dash. It indicates that it will be preceded by the number of zeros here. And if you observe that in exponent part we are getting the 11 bits exponent. That is the first problem which is we have solved. Any problem in this? Okay, what is E binary should be a 1 0 0. How it comes 1 1 0 0? Where is 1 1 0 0? E with binary. Yes, it is 1 0. 2 divided by 2. It should be a 0 0. Here it should be a 0. Correct. Other than that, any doubt? Okay, I will go for the problem. Like this only, we will go for the next problem. Now next problem is a small example is given 42.625. We need to represent these given decimal number into double precision format. Purposefully I am keeping these steps all how to convert all steps on one side and problem solve on the another side, so you can easily see the problem and solve according to that. So first of all, for the given floating point number 42 is an integer number, so we have to follow to convert given floating point number into the binary. For integer part we have to follow the different method, and for the fraction part we have to follow this different method. So 42 is an integer number. So whenever we want to convert any decimal number, integer decimal number into binary, we need to follow the divide by 2 operation. So 2 divided by 42 operation will be done here for the integer, and this arrow indicates the how we can present this bit for the 42, which is I have written here. For 42 it is coming 1 0 1 0 1 0, like that answer we are getting. After that, for the fraction part, 0.625 multiplied by 2, we need to perform for the fraction part of the given floating point number, which we need to convert into binary. Same steps we have to follow. 1 point, it is giving you answer 1.35250, sorry. Then again, point fraction part we can take for the multiplication, multiply by 2, we can get the answer 0.70, again 0.70 multiply by 2, like this we can do. And after performing this up to 3 decimal point, minimum 3 decimal point we have to do. Here I have done the more than that, it doesn't matter. So whatever after performing these multiplications, whatever integer value is coming in form of 1 and 0, we have to represent separately. And whenever we are writing the total answer of the floating point number of given decimal number into binary, we have to use the top down approach. That means for the given 0.625, binary representation is 1010110, like that we can put here. So total this 42.625, this decimal number binary representation is 101010 dot fraction part 10110111011, like that it is going to continue for the, if you are taking the more than that number of bits are taken, if you are taken multiplication modes here up to 3 digit, if you are done, that is also okay, no problem. But here I have taken the more than that. Now second steps, which is we need to perform after conversion of given decimal number into the binary, normalize the binary number, and we need to find out the value of sign, exponent and mantissa. Now normalize the given number. Here this binary number is given, we move to this decimal point after before this 1, sorry, before this 0. So we can get the answer 1.010101011, all these numbers we can write down. How many positions we are shifting this dot operator? 1 2 3 4 5. So I have written multiply by 2 raised to 5. This 5 indicate the exponent of that particular number. So sign bit, this number is positive, so I am writing sign bit is 0, exponent is 5, and after decimal point, whatever data is remaining in a form of 1 and 0, that total data is called as a mantissa, which is I have written here. That will be a second steps we have performed, as well as the third step, that is if sign number given number is positive, sign bit is 0, otherwise 1, that also I have done here. Now fourth step is that bias double precision format, which is I need to follow, that is a E dash is equal to E plus 103. Here exponent in double precision format, exponent is access 1023 code is there in sign number representation. If you observe that yesterday's lecture, in single precision, exponent is access 127, access code is used for the representation of single bit precision. Here double bit precision, access 1023 code is used for the representation of exponent. What do you mean by the access 1023 code? That is nothing but if you are having n number, adding that particular n number to the access code of that particular value. For example, we are having the access code, we need to find out the access code of 1023. See, so 1023 plus that particular number, it will give you access code of that numbers 1023. Now we have to apply the formula E dash is equal to E plus 1023. What is your E value? It is having value 5. So I have taken the 5 value. Then 1023, the access code of exponent we are going to find out. So use access code of 1023, we are getting 1028. Now this number is in a decimal. Again we need to represent that number into binary, which is we can do done in a fifth step. So total number is integer, so we can perform the divide by 2 operation of that total number and the represent the number of bits are represented, and this arrow indicate the how we can represent that particular bit. So 1028 we can get the answer 1 times 0 1 double 0. That will be a binary representation of 1028. After that, last step is that we need to represent the all these data. S is 1 bit, that is sign bit, to represent the 0. Then next one, 11 bit is your exponent and 52 bit is your mantis, which you need to represent here. So that will be a final answer. Any doubt in this? Any doubt? Student, any doubt? No. Okay. I will go for the next example. Then now we will move to the next example. In that small example is there, it is given that the 12.5 you have to solve using the double precision format. So for this smaller number, if you know directly binary representation, directly you can write down. For 12 we can get the 1100 dot. After that, for fraction part you need to find out the 0.5 multiplied by 2, it will be give you 1. Again 0 multiplied by 2 is 10. So which is I have written here. Then we have to go for the second step, that is the normalization steps. In that normalization steps, we need to move this decimal point after this 1. So first one we need to move. So how many bits you are moving? 3 bits. So I have written 1.10010 multiplied by 2 raised to 3. Now depending upon that, we need to find out the values or the values of sign, exponent and mantissa. So sign bit in this number is positive, so we can represent the sign bit value 0. If exponent here exponent value we are getting the 3s, which is I have written here, and after decimal point this will be a total mantissa, that is a 10010. That will be a mantissa. After getting this value, we need to move to the next part, that is a bias double precision format. In this bias double precision format, it uses the exponent value of access code of 1023. So for that we can use the formula E dash is equal to E plus 1023. What is E value? E is having value 3 plus 1023. We can get the access code of 1023 2026 for the 3. Now all these answer we are getting in binary, we need to represent in the format in a form of ones and zeros. So this exponent value of dash, we need to again convert it into binary. That will be a fifth step, which is total integer number. So we can divide that particular number by 2 and we can get the answers. We get the answer 1100111010. That answer we are getting. After that, last step, we need to put the value of sign, exponent and mantissa. So sign bit is 0, it will be represented here. Exponent is written here, total exponent, and mantissa is written here. Here sign bit is 1, it is okay. For exponent we are getting the 11 bits, it is also okay. But in mantissa we are getting the only 5 bits. Total 52 bits are there. For that bit, I have written the dot dot dot. That means here it will be preceded by the number of zeros are there for the remaining bits, or you can write down the number of zeros here. That is up to you. That will be your answer for the given problem statement. Now, instead of this, if this number is given as a negative, for example, minus 12.5. you need not do anything. Only the one steps you need to change in the third step, that is the s is equal to 1, you need to set that change you need to do. And second change, while representing the answer s is equal to 1, that change you need to do if any negative number is asked in examination. That's it. That is the difference between the positive number double precision representation and the negative number double precision representation. In the third step and the last step, we need to set s is equal to 1. That's it. Any doubts in this? Any doubts, students? Student, any doubt? No. Okay. We will move to the next example. For example, in bigger number is there, they have given the different way, single precision and double precision, that is given in a books. It is little bit difficult. Here the we know that the binary number 4-bit binary representation and hexadecimal 4-bit representation of 0 to 9 is same even for the alphabet 8 in a decimal number 0 to 9 binary representation, and 10 to 15 is there. Okay, 10 to 15 is there in a binary number system is there. For that we can get the number representation which is same like the hexadecimal by representation of 4-bit, that is a 0 to 9 we can represent it the 4-bit representation as it is. For 10 onwards, binary representation is same for the hexadecimal, that is a 1010. But in terms of the hexadecimal number system, if you want to represent, it will be 10 will be replaced by the A. Then B is replaced by 11. So what is binary representation of 11 is 0, 1, 0, 1, 1. That is 11's binary representation. Same is in a hexadecimal. Then for C, it will be represented by the C is replaced by 12 in decimal, and then its representation is 1100 like this. So we can say that the 4-bit binary representation of 0 to 15 numbers as well as the hexadecimal number system is 4-bit representation is same. So here instead of performing this 1259 this huge number operations, they are given the shortcut. So what is that? The here we need to find out answer in a shortcut way. So 16 is in a hexadecimal number system base. So for the given number, it is divided by 16, and we are keeping the reminder tag. That will be a nothing but you can get the value of mantissa. Then how we can find out the value of exponent? That value is 78. So again for this 78, it is divided by 16, and we can find out the answer. Whatever remainder is coming after performing this the answer of division, that is nothing but the exponent value E is represented. So for this E, C, it will be represented. E means E is written here, and B is nothing but the whatever remainder you are getting there, that will be put. So next step is that after performing this operation, next we need to represent all this data into the bit format. So for the fraction part, 1 to 5 multiplied by 2, that operations we have performed, and total answer is again performed in the binary format. Here first of all they have solved the single precision format, and then after that the double precision format is solved. That is given in a book, but it is little bit difficult to understand these all these steps. Better way, previously whatever steps I have explained in the slide, you can refer that. Do not refer this slide. For your reference I put in the in this format. Do you feel that I need to explain second method, that is very complicated to understand all these concepts? it is time consuming as well as the complex. So first of all, whenever, as I said that the we have seen the format for the double precision. Here one sign bit is represented, as I have said that the exponent in the book, it is written in one book, amateur book, they have given the same format, and the another book is there, in that it is written that the exponent is E, exponent is nothing but the excess code of 1023, which is they have written in the format itself, but most of the format it is not written. And 52 bit is mantissa, all these things are written. 0 to 53 is a mantissa, and 54 to, sorry, 52, total 52, 51 bit is there, sorry, here 51 should be there. Total 52 bits here, from 52 to 63, total 11 bits are exponent, and from 62 to 64, last bit is there, that is a sign bit which is represented here. Only they have mentioned that if sign bit is 0, that means it is a positive number, and if sign bit is negative, that it will be represented by the value 1, that is given in the format. That's it. And for the single precision also, instead of XS 1023 code, they have written the XS code of 127, that code is written. That is your end of your unit. Any doubt in second unit, please put it and tell me. Second unit, any doubt is there? I will go to the slide, total second unit syllabus. This is the total syllabus of your second unit. Any doubt in any point, you tell me. In the most of the things are logical, and numericals are there. Any problem? First unit and second unit, you may receive the today only. You are having the CAE 1 tomorrow for the all three subject, and what will be the pattern that will be circulated through the exam coordinator today itself. Start studying the all three subjects. Even in the next month, second or third week, you are having the end same examination of the all these three subjects. Any doubt? Another thing is that those students are absent for the TAE 1. They can submit the handwritten assignment in Google Classroom. Scan it. Handwritten assignment, scan it by mobile, make it PDF, and give your roll number there. And then only I will consider their students' marks. Anything, any doubt? Please tell me. No doubt. First unit, second unit, no doubt. Now for third unit is very small. It will be finished within a 2 to 3 lecture only. Fourth unit required a more time. Okay, ma'am, Booth's multiplication of 5 multiplied by 4, that you need to explain. Okay, I will share again. I will see the PPT, and accordingly I will share. Okay. Uh, okay, I will share the screen again. I think it is in 12th lecture. We'll see. Yes. This one. Okay, Mansi. This one. Am I right? Mansi Maurya. Okay, 5 multiplied by 4. This you need to repeat again. Here, 5 multiplied by minus 4 is given. Multiplicand is 5, which is represented by the 4-bit representation, and multiplier is a minus 4. That is, a multiplier is nothing but it is a Q register, and multiplicand is M register according to this both algorithm. So A register, Q1 register is initially having the contents 0. M indicate a multiplicand, Q indicate the multiplier, and counter is equal to N. So counter I have written here. Counter is N, that is nothing but the number of bit which is we are represented that particular number. So 4 counter I set. So A register is 4-bit registers, zeros. 4-bit representation we are taking as a 4 zeros. Q register is minus 4. Minus 4's 2's complement we need to take. So 4 plus 4 we have represented 0, 1, 00. Then first of all we need to take the ones complement of this. So 0 is replaced by 1, 1 is replaced by 0, and all zeros are replaced by 1. So we can get the ones complement of plus 4 is 1, 0, 1, 1. In that we are going to add 1. So in ones complement, if you add the 1, we can get the 2's complement. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. Again 1, 1. So we can get the answer 0, 0. This is 0. Okay. So we can get the minus 4 in a 2's complement form. That is a 1, 1, 0, 0. And Q minus 1 is we are representing as it is. So this is a first step. That is I have done initialization steps. Now we are moving to the according to flow chart. We reaches to the next condition box. That is Q0, Q minus 1. So here what is the Q0 and Q minus 1 value is having? We are having Q0 is 0 and Q minus 1 is
7.2 mm चा डायल आहे.
मोठा आहे.
तिचा हात केवढीच आहे पहा.
तुझ्यासारखा
Q0 is 0.
तिच्या हातावर आणि
Yes. Mute yourself. Yes. Nala power.
Sorry, ma'am.
Then if you check this 0, 0 is there, Q0 and Q minus 1. So Q0 and Q minus 1 is 0, 0. That is a second condition. Second condition is there. So in that, from that condition box, we move to the next decision box. In that arithmetic right shift register operation of A, Q and Q minus 1 we need to do. So I have written in a short arithmetic shift right, ASR. So for this A register arithmetic right shift operation, how we can perform? MSB bit is 0. I am keeping as it is. From MSB bit, we are shifting 1 bit right position for the destination data. Like this 0 go to the this Q register here, and this Q0 becomes a Q minus 1. After performing these operations, we need to decrement the counter. Counter is initially 4. We need to decrement that counter. Counter becomes a 3. Here we go to the next condition box. We can check the counter value is equal to 0. No. So again, according to these arrow positions, we go here. Again, we reaches to the condition box and check the value of Q0 and Q minus 1. Again, we are checking the value of Q0 and Q minus 1. It is 0, 0. Again, we need to perform arithmetic right shift operation of this A, Q and Q minus register. So A register MSB bit is 0. It is keeping as it is. From A register, we are moving the content in the right 1 bit right position like this. This is indicated by arrows. Then lastly, Q0 becomes a Q minus 1. So again, we need to decrement the counter. So counter becomes 2. Then we can check the counter value. It is not 0. Again, we will move to the next according to this arrow. Again, we reach to the this Q0 and Q minus 1 conditions we are checking. Now we are getting the Q0 is 1 and Q0 minus 1 is 0. So 1, 0 is there. So we need to perform A is equal to A plus M operation. So A is equal to M operation we need to perform here. So A is initially 0 and what is your minus M value? That is a multiplicand. Multiplicand. Anand, roll number 22, switch off your mic. So 5 minus 5 value we need to find out. It is coming 1011. This value M minus M value we are getting, that will be subtracted from the all 4 zeros. So we are getting the same answer. 0 minus particular number, we can get the same number answer. So I have write that things, and remaining Q and Q minus 1 I have represented as it is. After performing this, A is equal to A minus M. I am writing the going for the next step. Next box, that is arithmetic right shift operations I need to perform again. So in the MSB bit 1 is there. I am keeping 1 as it is. From MSB bit I am shifting each bit in the right position like this, which is indicated by arrow. So this Q0 bit shifted to Q minus 1. That I had done. Then again I need to decrement a counter. Counter is 2. It becomes a 1. So it will be checked to the next condition box. Counter is equal to not 0. Again we will go here. Check the condition Q0 and Q minus 1. Q0 and Q minus both are having 1 bit. So directly this is 1 bit. So again we can perform the arithmetic right shift operation. So arithmetic right shift operation, MSB bit is 1 as it is. MSB bit, we are shifting the each bit 1 bit right positions. So like this we have shifted. So last Q0 bit becomes a Q minus 1 bit. That will be done here. Then we will decrement the counter. Now counter becomes a 0. Again we reach to the next condition box. That is a counter is equal to 0. So in this counter is equal to 0. This condition is satisfied, yes. So we will end the operation and this remaining will be the answer. Out of this, Booth's algorithm or Booth scientist says that whenever you are performing these operations, multiplication operation with the help of this algorithm, that time whatever contents is in A and Q register, that will be answer. So 5 multiplied by minus 20, sorry, minus 4, we can get the answer minus 20. So whatever answer, that is a 1110 and 110, that answer we are getting, it is in a 2's complement form. If you want to verify that particular answer, you have to convert it into its original form. So what is your answer? 1110 in A register and Q register 1100. That will be answer. So first thing is that you have to take the ones complement of this particular number. So 1 is replaced by 0. All these 0 we can put, and 0 is replaced by 1. That I'm doing here. That is the ones complement of this particular given number. Now after doing this, I need to add 1 to this given number. So it will be give you its original form. 1 plus 1 is 0. Carry 1. Again 1 plus 1 is 0. Here carry 1. 1 plus 0 is 1. 0 as it is. 1 as it is. 0 as it is. 0 as it is. 0 as it is. And if you see the positions of this, all these 1, that is weighted code which is we are going to use. For this, for example, this 1 is there. So we can find out the value 1 multiplied by 2 raised to how many digits? 1, 2, 3, 4. Then for this 1, 2 digits from there. So 1 multiplied by 2 raised to 2 we are getting. 2 raised to 4 we can get the answer 16. And 2 raised to 2 we can get the answer 4. So total answer is 20, and in front of that number, one of the number is negative, we can put the negative sign. Like this, we can verify the answer. Now understand? Okay, ma'am, who is putting? Abhishek Borsai put, madam, while going from the counter 4 to 3, why we are doing 2 times arithmetic right shift operation? We have not done the 2 times arithmetic right shift operation. When we can do the right shift operations, whenever we are having the, I will remove this. If we cannot do the 2 times, that is totally depending upon the Q0 and Q minus bit, this condition box. Here, if you observe that, I will, okay, I will move this box once. Here, if you observe that initially we are getting the annotation. Initially we are getting the Q0 and Q minus value 0, 0. So this is first condition. So that I have done the first time arithmetic right shift operation. Then again I am getting the 0, 0, that value. So that again second time I have done. Now understand? Yes. Understand, Abhishek? Then second one is Mansi Moore is asking, ma'am, every time for every multiplication for verification of answers, we have to do the 1's complement plus 2. Not necessary. That I am going to show you how to verify the answer. Whether in examination, if you find out the answer and your answer is correct or not, that verifications you can do from your side. That's why you have to do it. There is no need to do it 2's complement of that particular. If the either multiplicand or multiplier is negative, that time multiplication answer is negative. Means here 5 multiplied by minus 4 is there, so answer is minus 20. Or reverse way is there, minus 5 multiplied by 4 is there. Like these conditions are there. As I said that the multiplicand or multiplier, one of the number is negative, then only answer is negative. That time you have to do it. And another thing is that if both numbers are negative, that time also, for example, minus 5 multiplied by minus 4 is there. You can get the minus that plus sign here, plus 20. Here means in these two condition only, if you want to check the answer is correct or not, that time only you can do it. Any doubt other than this? Yes, his doubt is clear. Nancy, any doubt? No? Okay. Best luck from for tomorrow's exam. CAE1 exam. First 2 units are completed. This PPT, last lecture PPT, yet I have not uploaded. After completion of this lecture, I will upload this last lecture PPT. Okay.